we were looking at in the last talk, at least in the first part, an improvement on that, with the amplitudes in the average. Yeah, go ahead.
Yeah, thank you very much. Thank you very much for the invitation, organizing this workshop, and for giving me the opportunity to present what we did here. So a little bit of an apology to those for already 2 years ago. So the progress is obviously, usually we want to have more progresses, not so much as we wished, but I think we developed a better understanding of actually what we are doing. And I think this is also something to be worthy. And this is what I'm focusing mostly here. So I try to extend on what we've done, and from the basic phase averaging to higher order and what actually is happening, and right. And so I'm focusing on this in this talk, and as it's written here. So it's collaboration with Colin and Beth and of course others. Okay, so there's a couple of things that I want to mention. First of all, the motivation for phase averaging. I don't have to say much because Juliane already explained it quite nicely. So I just repeat it and put it into my notation. Then I actually mentioned the idea of higher order phase averaging and what are the research questions that we are addressing by doing this. And I want to, and we will see that at some point we have to select a model, right? So I used to change this now because when we have now this general equation, this higher order phase averaging, we need to select a model before we can actually, before I can actually explain more. So this is why now the selection of the model is quite early in the talk. And then I will explain on 2 examples. You already remember we have the monomial expansion and the exponential expansion. And then I show some numerical results. Okay, let's start with the motivation. So why do we do those? Does this work? I use the mouse. So phase averaging, right? So why do we want to have an approximation of a high oscillatory PDE by probably a slower one, right? This is good for either for analytical studying, right? It's easier to track a slow PDE, so we can have you can use mine. Oh yes, this is nice. Thank you. So thank you very much. Analog. This is what I like. Exactly. No, exactly. So first of all, we can approximate a nonlinear PDE by a slow one. This is good for analytical study, right? So I don't go into this detail today, but we can filter out fast motion. And this is important either for having larger time stepping or also studying analytically. And the idea behind, I cannot go too much into detail because we are not so far yet, but the idea behind these things is, as we see, we want to have parallel computing, and we want to develop something for parallel computing. I mentioned a little bit about this, but unfortunately, we're not so far yet. So these are the ideas behind it, and I consider the following initial value problem. So I merged the 1 over epsilon into the L. For me, L is the fast one, linear operator, imaginary eigenvalues, and N is a bilinear operator. I write it like that, and then Juliane already explained that what we have, it's the modulated system that we have. And actually, when you look at, for instance, a solution of this one, go to the modulated system. On this, you would somehow see something like that when you average, you have something like an average solution, and on top of it, oscillations. And in my numerical part, I actually will show that this is actually what we see and what we want. So this one is something like where this oscillation somehow kind of mixed. But when you go to the modulated system, you are now finally see some kind of average slow manifold, and on top of it, the fast oscillations. So this is a little bit of a picture of why we want to do this and what we have to make. And what's important here is to see that we have the velocity depends on the time and on the phase. So let's write this one like that. So it's a 1-parameter family of solutions. And because we have now this phase here inside to somehow mitigate this one or to somehow get control of this, we can, for instance, average over the phase and then we come to average solution. This is what we do next. So for instance, we can smooth high frequencies. So these high frequencies that we have here come from the S. We integrate over, we have some kind of integration kernel. And then we have an average solution, I noted by bar. And this is simply the integral, and we have to evaluate the integral. But before we go to this, so this equation somehow incorporates three different regimes, let's say like that. So depending on t, so t is somewhat the integration window, which could be from minus t to t, but it depends on the kernel how you want to write it. Let's say it's going from minus t to t, and this one over t. Then we can, if t goes to 0, we come back to the original equation, for instance. So then we come back to this one. So we simply go back when t gets very small. And so also in the numerics, when I make t very small, I converge to the exact solution. So this is what we want, that we have some kind of consistency. Then when we go to infinity, right, t to infinity, we come to average, to asymptotic expansions. And this has been done in the literature. I don't go into detail of this. And what is the regime is interesting for us if the averaging window is finite. And it's as such as we want to have it so big that we somehow want to smooth out fast oscillation. So this is the idea that we want. And we go on this regime here where we have a finite averaging window. So the pathway to parallelization is now, this is probably the only thing that I talk about parallel in time, sorry, but as I said, it's a work in progress. So what we want is actually, we want to have large time steps, right? So large time steps, and then somehow jump up this large time step into kind of collocation points, and then have a sum and do this sum in a parallelization across the method style. So this is what we want. This is why we want to have large time steps, then having a lot of terms that we can compute in parallel. But for this, we need large time steps. Delta t should be a large time step, and then we can compute each of the term, hopefully in parallel, and having a good speed up by this one. So this is the idea why we want to do this, one idea. However, when we look at the original averaging, so that has been also started by Peddle, the error grows linear with t, but when we want to have, for stability reasons, when we use large t, also need a large time step, we also need a large t. So this is a little bit of a problem. And so as larger t gets, as larger the error gets. And this is the reason why we want to somehow try to improve this, having large time steps, having large averaging windows, but reducing the error. And here the higher order phase averaging comes into play. Because what is the underlying assumption of this higher order phase averaging? The assumption is that within this averaging window, we assume that the solution is independent of the phase. We average over it, right? So S is insensitive to changes in S. When we move our solution around, we integrate over it, it shouldn't change. But this is a good assumption. And we see that we have errors when we do averaging. So maybe it's not the perfect assumption. Maybe we can improve it. And what error does this introduce when we assume this insensitivity? So these are a little bit the research questions that we followed. Okay. And then it comes the central idea of higher order phase averaging. The starting point is again this one, this equation, right? But rather than assuming that this depends not on S, not on the phase, we say that we parameterize the dependency of this of the solution. The solution is solution can be anything, a velocity and height field. So, but we assume in a shallow water equation, for instance, we assume that this that we can parameterize the dependency of this solution in terms of S. So we say we have a basis vector that depends on the phase S, and this is going to be selected later on, and I give two examples. And then that the dependency of the solution is parameterized by the solution that does not depend on some kind of basis. And we select some kind of what order of what order of approximation we want. The next step is that we present this dependency of the equation by projecting this equation onto this basis. And I show you on the next slide what I'm doing. And important is that in this picture that I've just shown you, the standard averaging assumes that we just don't, that this is 1 and this one does not depend on S. And I will compare then higher order results with the standard results, where we always see when I switch on n or n minus n plus or n to be 0, it's then the basis averaging. And then higher order terms are then the corrections. For instance, when the S is 1, so we have a linear correction or quadratic correction or whatever. Okay. So, and this is now, let's assume we have this one. So now we say that we have a basis, that we have a space. The space is spanned by the basis that I just explained. So by a basis that represents the phase. And we expand our solution and the test functions in terms of this basis with coefficients that only depend on t. This one depends on the phase. And then we project equation 2. I just had a bug, right? Here it's equation 3. Sorry, it's actually equation 2. This equation, sorry, I messed this up. It's actually equation 3. That will check this equation onto this basis, and this is what we come to. So, right, it's the inner product of when we develop the test function. So this is now the test function part. This is the solution part. We have the basis vectors, and we sum over it, and we have some kind of integration kernel. And here we have two terms. This will be a mass matrix that somehow couples the different modes with each other. We will see this later. Different modes are now coupled. And then here, the right-hand side is going to be, it depends on these 3 basis vectors. Why? Because I assume we have a quadratic nonlinearity. Each of the terms has its basis vector. And and here we have the basis for the test function. Okay, so this is now the so from the general idea, this is the most general way of what we developed so far. So this describes actually what we want, and to go further, we somehow have now to specify what this is. Otherwise, we don't see anything, right? So this is what I said here. So we need to specify the model. So I think the swinging spring model is as well known now. So the swinging spring model is a pendulum that goes like that, but it has a spring, so it goes like that. And by a nice selection of frequencies, it swings like that, and it has a precision, so it does like that, and then does like that. So it has some kind of makes a star shape, just because when you select the nice frequencies. And so it's an interaction between the two frequencies, WR and WZ. And when you select them nice, you have a very nice precision. So this is just a nice model that models a geophysical flow, because what we have here, we have somehow fast oscillations that have, by interaction with the slow modes, it somehow leads to a large scale oscillation. So this is why it's an interesting model for us to start. And the other part, the important part, is that we actually can represent this model, which is an ODE, in terms of this modulated system, right? So we can write this one with a fast and a slow part, nonlinearity, and we can write this model in terms of what we want. This is what I'm doing on the next page. It looks a little bit complicated, but sorry for this, but you don't have to understand the detail. The take-home message from this page is that the ODE, the swinging spring ODE, can be represented as we like it. And every time when you see these coefficients here, it's just the nonlinear terms, these two quantities, the two velocities, and these coefficients somehow tell us that this is a different term of representation of the higher order representation of the nonlinear term. These are just some coefficients that we need to represent the ODE spring. So there's the L and M somehow depends the higher order representation of the solution. depending on the phase. And this kappa is just, we need more of these terms to represent the swinging spring. So this is it. And you see the Z components, these are the velocity, also the V is not velocity, sorry, it's the modulated solution V. When I talk about V, it's the modulated solution. When I talk about U, what I had before, it's the original model, the original spring where you see actually the pendulum swinging, but the V solutions will look quite different. But on the V solution, you will see the oscillations on top of the slow manifold, whereas on the U you wouldn't see it. So I just give this as a preparation for those slides when I go to the numerical resolutions, to numerical solutions. And the set head components are those that are X, Y, and Z of the modulated solution. And these are just a couple of coefficients that we need to represent the swinging spring in this term. And as I said, I just want to show that the nonlinearity can be represented like that, because later on, when I do now the discretization, you will see that these terms appear. So there are two expansions that we studied. The first expansion is where we say now, okay, the dependency of the velocity of the solution vector, the modulated solution vector, should be here represented as monomials in S. So we select the basis vector of this S to be simply S to the power of K. And the same for the test function. We can put this into representation that I gave you above. And then we have this kind of terms, S to the power of J plus K. J comes from the test function. For all J's, J comes from the test functions here, right, guys? So, and then we have K. K is now the representation of the trial function. So you see this will be now a system that depends for each J, it depends on a couple of Ks. And I show a matrix representation on the next slide to show you how this system looks like. And this right-hand side, for each J and K, we can compute these terms. And this is what we did in our 2022 paper. We analytically computed this one. But if you do now numerics, more complicated system, this will be Gaussian quadrature. So, and then you will have a lot of terms that you can do again in parallel in some sense, right? So this is the idea. You have a couple of sums here, and then also these integrals were going to be evaluated as sums, and this is where this complicated system then, with a large time step, many stuff can be computed in parallel. So this is the idea why we do this, right? Having very large time steps, everything can be computed in parallel, and then gaining speed up by that. So this is the monomial basis, and when you look at the system, how it looks like, so this is what I just said, it will be a matrix equation. What you will see, this is like a mass matrix. What we see is when we have the V0 will be the solution we are interested in, but this V0 is coupled to higher order correction. So I see it like V0 will be the solution that we are interested in, but by coupling to higher order modes, there will be a correction of the solution. And I just showed the V0 part because the other one looks complicated and we didn't see much benefit in presenting it. And the right-hand side can compute it. There are just a couple of terms, but we can compute them analytically here, as I said. So we showed this in the paper, but we would use numerical quadrature. So the system would look like that in this case. So we have this matrix that couples the different mode. This would be the mode where we are interested in, and then it would couple the 0th mode with the 2nd mode and the 2nd and the 4th. This looks a little bit, so this looks a little bit complicated, but this we can bring on the right-hand side. And what we would have is we would have three orders somehow of solutions. The time evolution of this term here, which is of interest, would somehow be a coupled system where this term evolve in time and they feedback over the right-hand side to the evolution of this one. And you will see that this term and the interaction of these things actually corrects this term and makes it more precise. It looks quite complicated. It was a little bit complicated to implement, but it works. And this is what we wanted to show. And then let's go to the exponential basis. What do we want to have here? So rather than having the monomials, because the monomials somehow approximate the phase at a point in some kind of monomial way, and it doesn't really go over the next bump if you have oscillations. So it didn't really, and you will see later, it didn't really work out. That averaging window had to be very small. So the idea was that we have something like a Fourier representation of these phases that go quite large. And so this is what we've done then. So rather than using the monomials here, we used exponentials that are somehow scaled by the L operator, by the linear operator, like that. So this is what we put here in, and then we come to this system. So here, these integrals can also be computed analytically. So we did this. It all comes from the original projection idea that I presented in the beginning. We don't have to go through details. What it's just important is that all these things can be computed here. And here we have still a coupled system that I show on the next slide. So what do we have here now? We have here now a system. This matrix couples the different velocities together, right? So maybe I explain it here. So what we have now, because this is kind of a Fourier exponential Fourier representation, we have the zero mode that we are interested in. We go from -n to n. All these Fourier modes around the zero mode somehow contribute to correcting the zero solution. And this is what you see here now in this system. So we have the -1, the 0, and the 1 solution. So this is where we are interested in. But the matrix here with these exponential terms somehow couples these things. You see when we go, so when this is this matrix here, somehow it selects this one to be the value of interest, then somehow the other modules, as far out they go, as less they contribute, something like that, when you look at this one, right? So it made sense. So the further outside you go, the smaller the contributions are. And the right-hand side is now this vector that can also be computed because we have all the values. Let's come to the numerical results. I think this was quick and it's quite technical sometimes, but take-home message anyway, we can read off from here. So this is the swinging spring when we project the swinging spring down to the XY plane. And this actually is now the solution U. So when you look at the normal solution, this is how the pendulum goes back and forth. And when we look, so you don't see any difference here. So this is why I zoomed in. So this would be the exact solution. This is the modulated solution without any averaging would be the blue. So when you take normal averaging with a large T, so we would have something like an error of this in the precision, right? So it would, after one turnaround, it would have an error of 10 to the -2, something like that, or 10 to the -3. But when we do higher order corrections, we can actually make this much better, right? So actually we can improve the results by adding these higher order corrections. So it does improve significantly the accuracy already when you look at this one. So when we look at the V solution, so this is now when we look at the V solution, these are this capital V, and here we see a X, Y, and Z solution. Let's focus on X. And you see when we go forward in time, here you see differences, right? For instance, this blue here is the averaged version, and then the orange one here is, or the blue one here, it's lying over the exact solution, because when we take here, I don't remember, maybe higher or something, or I forgot to write it, probably n equals 10 here. So we have or 5 or 6 correction terms, then we go also closer to the true. So this is the time evolution of the V field, right? So And you see particularly here that after long integration times, they differ, right? So we have a drift, which is known from this averaging method, that we develop a drift when we run them long. And what you see here is now actually on the V solution, you would see the averaged solution here and the exact version where you actually see also now in numerics that the averaging actually smooths these things out.
So both of those are in the modulated space.
Yes,
Right.
this is the modulated
So
space.
this is the oscillation on top of the modulated.
Exactly, exactly. When we switch on smoothing, right? So this actually, I probably it's not very visible, right? Actually, this is actually the blue one is actually the exact solution, only the modulated one, and the red one is the smooth, where I had an averaging window of 2, 3, 4. I don't remember anymore. And then when you now switch on higher order averaging, we would somehow recover these oscillations. And I say something about this in the conclusion. But what we see is that this thing is very high sensitive to small oscillations, right? So when we don't somehow resolve the small oscillations in the beginning, so we will have a big drift. So this is what I wanted to say. And our higher order system can somehow correct this by taking these interactions between the higher order modes and the zero order mode together. So this method works. It really improves the stuff. What I want to let's go back to the monomial basis. So when we I speed up. Sorry, in 2 or 3 minutes I'm done. So what we see now for the monomial basis, right? So when we increase the order of correction somehow, so this is 10 correction terms somehow. So what we do, we recover these high oscillations, and then when we recover these high oscillations, we reduce the drift in the end. Yeah, so this is what's happening here. But in the monomial case, the problem is when we make the averaging window bigger. So this is now a plot where we show the order that we take, the order of corrections, higher order terms, versus the averaging window. And the averaging window in this case here in the monomial, it has to be very small, but it's not very satisfying. Just said before. And even when we go here to, for instance, 0.5, so we gain a little bit of accuracy, but it's not sufficient. So this is where we said then, okay, in principle, it works. We see that we can somehow correct, but the averaging window was much too small. And then we thought, okay, let's try the exponentials. What's happening with the exponentials now? So this is now the plot again from this V plot, and we look at the first time steps. What we see here now, so when we correct, this is kind of what I said before. First correction is very large, and we somehow, these oscillations are again corrected back when we add higher order terms. At some point, when we have 0, 0 is the averaged version, where we don't correct. And we have the green is the first one. You see that it starts to have a little bit of these oscillations around the averaged version. Then we have the second version here. And at some point, it actually goes back to the oscillation. And then you also see that in the end, a drift that has been here averaged has a high drift. And then as further down you correct, as further down you, as better you get the drift reduced. So, but the difference to before, so we also get these oscillations back, but the difference to before is that now this thing does not depend on the averaging window size. So this is what we actually wanted. So we can, with high order terms, so we can go up to 10, 15, 20. When we have somehow 15 correction terms, we can have an averaging window of 20. And this actually does not depend on the size. So this is what we wanted. Right, so we were quite happy, and this is also an update from the former pictures from my last talk, because these pictures are now really what we want to see. So we can converge to solver tolerance by just adding up and up more and more things. So what do we see here now? We have something like we add a parameter in the possibility to play around with these things, right? So we can now fix the averaging window and can correct back by keeping the averaging window big and we have a new parameter where we can somehow reduce the error by adding more higher order terms. Before, when you just look at the averaging, you have to reduce the averaging window to reduce the error. So this new flexibility gives us now the possibility to work on a decently large averaging window T and having smaller errors. But the problem that we have is, I'm going to say this now on the conclusion part. So we developed this higher order phase averaging method, and the essential part is that we go to this modulated system, where on top of the averaged version we have the frequencies. This we can smooth out. And what we did, this higher order expansions, in particularly the exponential basis, helped us to have a fixed, large time averaging window and reducing the order by adding more terms, more correction terms. The downside here is, and what it took us so long that we didn't have new results. I think we tried a lot of integrators. We implemented spectral defer correction method and here and there, and we always brought somehow back these oscillations, right? So, and then at some point we also realized, which may be a little bit naive, but in the end we realized the model is not complex enough, right? So, because the point is when we want to reduce the error, we need the second oscillation, right? At some point, this is what we realize. So the point is, what we go next is that we need a model. Probably what we try to do is this wave radiation mixture of an ODE PDE. That's Vanest suggested this, which is a combination of an ODE PDE, where we can work on this one. And then also what I said, we want to implement kind of a parallelization across the method for what we have so far, right? So with this, I thank you for your attention, and I'm happy to take questions.